Hello friends, welcome to this YouTube channel. Today we are going to solve one numerical problem on three-phase medium length transmission line. By solving this problem, we shall learn how to determine generalized constants A, B, C and D of a three-phase medium length transmission line based on its nominal T equivalent circuit when transmission line parameters are given. We shall also learn how to compute percentage voltage regulation and efficiency of transmission for this line using these constants when load details are given. A 200 km long three-phase 220 kV 50 Hz transmission line transmits a load of 75 megawatts at 0.8 power factor lagging at the receiving end. Resistance per phase per kilometer equals to 0.8 ohm. Inductive reactance per phase per kilometer equals to 0.8 ohm and capacitive susceptance per phase per kilometer equals to 6 micromole. Using nominal T method, we have to compute ABCD constants of the line, sending end voltage and current, sending end power factor, sending end active and reactive powers. We also have to compute percentage voltage regulation and efficiency of the line. Let us first write down the given data. Power delivered to the load PL equals to 75 megawatts, that is equal to 75 into 10 to the power 6 watts. Line to line receiving end voltage via line equals to 220 kilovolts, that is equal to 220 into 10 to the power 3 volts. For star connected system, receiving end voltage per phase VR equals to VR line divided by root 3, that is equal to 220 into 10 to the power 3 divided by root 3, that gives us 127,017 volts. Given load power factor cos phi L equals to 0.8 lagging. Let us now determine power factor angle. Phi L equals to cos inverse 0.8, that is equal to 36.8699 degree. Expression for power delivered to the load PL equals to root 3 times VR line into IL cos phi L. Therefore, load current IL equals to PL divided by root 3 times VR line into cos phi L. Using values we get 75 into 10 to the power 6 divided by root 3 into 220 into 10 to the power 3 into 0.8. That gives us 246 ampere. Load current may be written in polar form as IL equals to IL at an angle minus phi L, that is equal to 246 ampere at an angle minus 36.8699 degree. In this case, load current IL equals to receiving end current IR. Given length of the transmission line D equals to 200 kilometers. Resistance per phase per kilometer R1 equals to 0.8 ohm. Inductive reactance per phase per kilometer XL1 equals to 0.8 ohm. And capacitive susceptance per phase per kilometer VC1 equals to 6 micromole. Now we shall compute resistance per phase R equals to R1 into D. Using values we get 0.8 into 200, that gives us 160 ohm. Inductive reactance per phase XL equals to XL1 into D. Using values we get 0.8 into 200, that gives us 160 ohm. And capacitive susceptance per phase BC equals to BC1 into D. Using values we get 6 into 200, that gives us 1200 micromole, or 1.2 into 10 to the power minus 3 mole. Series impedance per phase of the transmission line Z equals to R plus J times XL, that is equal to 160 plus J times 160 ohm. This may be written in polar form as 226.274 ohm at an angle 45 degree, and shunt admittance per phase Y equals to J times BC, that is equal to 0 plus J times 1.2 into 10 to the power minus 3 mho. This may be written in polar form as 1.2 into 10 to the power minus 3 mho at an angle 90 degree. We have obtained series impedance per phase of the transmission line Z equals to 226.274 ohm at an angle 45 degree, and shunt admittance per phase Y equals to 1.2 into 10 to the power minus 3 mho at an angle 90 degree. Now we shall calculate Y into Z. Using values we get 1.2 into 10 to the power minus 3 at an angle 90 degree into 226.274 at an angle 45 degree. That gives us 0.27153 at an angle 135 degree. This may be written in Cartesian form as minus 0.192 plus J times 0.192. Now we shall compute 1 plus 1/4 of Y into Z, that is equal to 0.952 plus J times 0.048. This may be written in polar form as 0.95321 at an angle 2.8864 degree. For T equivalent circuit, A equals to D equals to 1 plus half of Y into Z, that is equal to 0.904 plus J times 0.096. This may be written in polar form as 0.9091 at an angle 6.062 degree. B equals to Z into 1 plus 1/4 of Y into Z. Using values we get 226.274 at an angle 45 degree into 0.95321 at an angle 2.8864 degree. That gives us 215.68664 ohm at an angle 47.8864 degree, and C equals to Y, that is equal to 1.2 into 10 to the power minus 3 mho at an angle 90 degree. Taking receiving end voltage per phase as reference, we can write VR equals to 127,017 volts at an angle 0 degree. We have computed receiving end current IR equals to 246 ampere at an angle minus 36.8699 degree, and generalized constants for T equivalent circuit A equals to D equals to 0.9091 at an angle 6.062 degree, B equals to 215.68664 ohm at an angle 47.8864 degree, and C equals to 1.2 into 10 to the power minus 3 mho at an angle 90 degree. Expression for sending end voltage per phase: Vs equals to A times VR plus B times IR. Using values we get 0.9091 at an angle 6.062 degree into 127,017 at an angle 0 degree plus 215.68664 at an angle 47.8864 degree into 246 at an angle minus 36.8699 degree. That gives us 166,906.61 plus J times 22,333.4 volt. This may be written in polar form as 168,394.17 volt at an angle 7.621 degree. And expression for sending end current per phase Is equals to C times VR plus D times IR. Using values we get 1.2 into 10 to the power minus 3 at an angle 90 degree into 127,017 at an angle 0 degree plus 0.9091 at an angle 6.062 degree into 246 at an angle minus 36.8699 degree. That gives us 192.0808 plus J times 37.88137 ampere. This may be written in polar form as 195.78 ampere at an angle 11.1565 degree. On no load, receiving end current IR equals to 0. Therefore, receiving end voltage per phase on no load VRO equals to Vs divided by A. Using values we get 168,394.17 at an angle 7.621 degree divided by 0.9091 at an angle 6.062 degree. That gives us 185,231.73 volt at an angle 1.559 degree. Now we shall calculate voltage regulation, that is equal to VRO minus VR divided by VR. Using values we get 185,231.73 minus 127,017 divided by 127,017. That gives us 0.4583 per unit or 45.83%. We have obtained sending end voltage per phase Vs equals to Vs at an angle delta equals to 168,394.17 volt at an angle 7.621 degree, and sending end current per phase Is equals to Is at an angle phi 1 equals to 195.78 ampere at an angle 11.1565 degree. For star connected system, sending end current per phase equals to sending end line current, and line to line sending end voltage Vs line equals to root 3 times Vs, that is equal to root 3 into 168,394.17, which is approximately equal to 291.7 into 10 to the power 3 volts or 291.7 kilovolt. Phase difference between Vs and Is, phi s equals to phi 1 minus delta. Using values we get 11.1565 degree minus 7.621 degree. That gives us 3.5355 degree. Let us now calculate sending end power factor. cos phi s equals to cos of 3.5355 degree. That gives us 0.9981 leading. Now we shall determine sending end active power. Ps equals to 3 times Vs into Is cos phi s. Using values we get 3 into 168,394.17 into 195.78 into 0.9981, which is approximately equal to 98.72 into 10 to the power 6 watts or 98.72 megawatt. Sending end reactive power Qs equals to 3 times Vs into Is sin phi s. Using values we get 3 into 168,394.17 into 195.78 into sine of 3.5355 degree, which is approximately equal to 6.1 into 10 to the power 6 volt ampere reactive or 6.1 megavolt ampere reactive capacitive in nature. Let us now determine efficiency of transmission. Eta T equals to PL divided by PS. Given power delivered to the load, PL equals to 75 megawatts. Therefore, eta T equals to 75 divided by 98.72. That is equal to 0.7597 per unit or 75.97%. So today we have solved one numerical problem on three-phase medium length transmission line. By solving this problem, we have learned how to determine generalized constants A, B, C and D of a three-phase medium length transmission line based on its nominal T equivalent circuit when transmission line parameters are given. We have also learned how to compute percentage voltage regulation and efficiency of transmission for this line using these constants when load details are known. Hope this lecture has been useful for you. If you have any suggestion or question, please drop it in the comment section below. If you have liked this video, give it a thumbs up and share it with your friends. Thank you.